In this video, I want to take a look at a specific test of really the first test, aside from looking at geometric and telescoping series, the first test whether a series diverges or not. Okay, and what I want to look at here first is this series, the sum from 1 to infinity of just 1 over n. Okay, this is actually called the harmonic series. It's a special series, and a lot of research has gone into this type of series. When we go out in our series here, we see the following thing: 1 plus 1/2 plus 1/3 plus 1/4, so on and so forth. And based on our previous kind of discussion, we were thinking about, a series converging when the terms that we're adding don't really go away. And that's what a lot of this video will be about. As n gets bigger and bigger, these terms in my series are getting smaller and smaller. But spoiler, this series actually diverges. Okay? And we'll show that in the next section with a specific test that we'll do to show that the series diverges. But what we can extract from this is hopefully a test to be able to tell when a series diverges or not. It's kind of based on the premise that the terms I'm adding further out in my series don't go to zero. Okay? So in short, it can be difficult really to tell whether a series converges or tell whether the series converges if it's not geometric or telescoping so far, right? With those, we have really quick tests. But there's another quick test, a quick way to tell whether a series diverges. Okay? And what that's called is the nth term test for divergence. Okay, and what I want to underline here is divergence. This is a test for divergence. This will not tell me if the series converges or not. And that seems a little counterintuitive, but it's just a quick way to determine whether a series diverges. All right, and it goes like this. For the series n equals 1 to infinity of a sub n, if the limit of that nth term there, the limit of a sub n is not 0, then the series diverges. Okay? And again, that's basically because the terms far out in my series do not go to 0. So as the series goes on, I'm adding terms that have some consequence, right? They're not enough to say, hey, the end of this series doesn't matter. We can say that it approaches a number. No, it's quite the opposite, is that at the end of the series, those terms are approaching something else. So when I add them to the whole, when I keep adding those pieces, it takes the series off to infinity or minus infinity if I'm subtracting. Okay? This is important, right? This test does not work in the opposite direction. This test does not work in both directions. Okay, that is to say, if the limit is 0, we don't know. We can't say. We say that the test is inconclusive. Okay? And the harmonic series is kind of our counterexample. Right? If we look at our harmonic series 1 over n, the limit as n goes to infinity of 1 over n is 0. But that doesn't mean the series converges. Okay, so it's very easy to fall into this trap of just taking a limit of this a sub n here and then saying, oh, it's 0, it converges. That is not true. And I haven't shown you how or how we know, but this series does indeed diverges. So we have to be a little careful here when we work with this nth term test. And I want to do 2 examples here. I want to show you where the test works and where the test doesn't work. But just pay attention and be careful. Determine whether the series converges or diverges. I have the sum from 1 to infinity of n factorial divided by 2 times n factorial plus 1. Okay? So one of the first things I noticed is this is definitely not geometric and definitely doesn't look telescoping. One of the quick things you can do is look at the limit, right? If this is our nth term, let's try the nth term test. Okay, so we'll take a limit of this a sub n, limit of this nth term. And I want to know then how to evaluate this limit. As n goes to infinity, we know n factorial gets really big. We talked a little bit about factorials before break. This factorial, as n gets larger, the factorial gets larger. And the numerator and denominator here are kind of close to the same order of magnitude, if you will, n factorial and n factorial. So let's see what happens. The difficulty here is that I can't use L'Hopital's, right? Because I don't know derivatives of a factorial. But what I can do is multiply both the top and the bottom by 1 over n factorial. And what that will do, sped up a little bit, is it will make this a little bit easier to evaluate. When I multiply the numerator by 1 over n factorial, those n factorials will cancel, and I'll have the limit as n goes to infinity of just 1 in the numerator. The denominator, this is very similar to the process of dividing through by the highest power of n in your limit there. So really the same idea. In the denominator, I see 2 plus 1 over n factorial. And as n goes to infinity, that 1 over n factorial goes to 0. So I have 1 over 2 plus 0, or 1/2, which is definitely not 0. Okay? That limit, the limit of the nth term, is not 0. So what that means, what that implies is in my series, right, far out in my series, I've got a bunch of numbers added together, but towards the end of my series, right, there's really no end, but far out in my series, I have 1 over n, or 1 over 2 plus 1 over 2. The terms in my series look like 1/2. They approach 1/2. So as things continue, I keep adding 1/2 over and over and over again. Well, if I keep doing that, there's no way that the series is going to converge, because I keep adding numbers that add to the series, that add to the overall sum. Okay? So really what happens here is the nth term test tells me that this series diverges. Right? This series diverges because the limit of the nth term was not 0. Okay, that's what the nth term test does. It tells you that far out in the series, the terms in my series start looking like some specific number that's not 0, so the series has to diverge. Let's look at another example. This time, n over 2 to the n. Well, I looked at 1 over 2 to the n before, and that was geometric. So this might also be geometric. If I go out some terms in my series here, I see 1, when n is 1, 1 over 2 to the first. When n is 2, 1 over, it's 2 on top, 2 over 2 to the n, 2 over 2 squared, plus when n is 3, 3 over 2 to the third, plus 4 over 2 to the fourth. I somehow skipped fourth and went to fifth. Let me fix that. That should be a 4. Plus so on and so forth. This is not geometric because there's not a common ratio, right? When I go from one term to the next, there's not a common factor that I'm multiplying each term by. So this is not quite geometric, and it's of course not telescoping. Let's try the nth term test. Try the nth term test. So as of right now, this is the only other test that we know. I'm going to take a limit of this nth term. Okay? Limit of n over 2 to the n. So this guy, it's his own limit. Basically, now you're in a limit problem. We got to try to figure out what the value of that limit is. Most of these will be indeterminate. Okay? Not always, but most of the time. This limit approaches, numerator goes to infinity, denominator goes to infinity. So let's try L'Hopital's here. I don't have factorials, so I can't actually take derivatives. I just have to be a little careful. When I apply L'Hopital's, I'm taking derivatives with respect to n. In the numerator, derivative of n with respect to n is 1. In the denominator, derivative of 2 to the n, we have to remember derivative for example, with respect to x, of 2 to the x is, let's do this in general, not 2 to the x, but let's say a to the x. Derivative of a to the x is a to the x natural log of a. So for our example, a is 2. A is 2. So what I get is 2 to the n natural log of 2. So what happens here is I made a mess of this. It would be a to the x. So what I see is that limit is actually 0. Right, as n goes to infinity, the numerator goes to 1, denominator gets larger and larger, the only n is in the exponent, and as that n gets bigger, the denominator gets bigger, which makes the fraction smaller. That 0 means my test is inconclusive. The nth term test is inconclusive. And that means that we're going to have to learn more tests. Because this series is not geometric, it's not telescoping. I could try to look at the sequence of partial sums. That's kind of the long way of doing things. Hopefully we'll find a shorter way. We'll have to be able to look at some other test. Okay, so the rest of this chapter is really working through learning more tests for convergence or divergence and learning those criteria and then being able to apply them to different series to tell whether those converge or diverge. Okay, thanks for watching.